This is the first video for 6-2, day 1, the definite integral. Part of what we're doing today, we want to review a little bit of notation so that when you see it later on in the calculus that you're thinking the same thing about that notation that you've always known from background information. So one thing you'll see today in notation is the sigma symbol. And sigma notation is for summation. It means we're going to add a bunch of things together. So if you need to pause, read this, and think about this a little bit more, stay on this page and do that, and then resume the video when you've gotten that refreshed. So one thing to make sure that you're thinking the right thing is we used these last year for series. That means we added together values that came from a sequence. So on this first one under try it, it says it would like us to add the third through sixth term coming from the function 2k. So what I would do first, this one's called a finite sum or a definite sum where I know my beginning and my ending. So I have to add together the values from when k is 3, the function value is 6, and that's what the summation is about, is adding. When k is 4, when that index increases by 1, when k is 5, and when k is 6. So the answer to this summation would be the total, and that total would be 36. Eventually, we moved into, last year, adding infinite values together, meaning every single value that comes from a sequence. So in this case, this would be the sum of all the even numbers. When k is 1, when k is 2, when k is 3. Some infinite summations will settle on a single number. Last year we said that happened when they converge. Okay, some will not, this one wouldn't. So what we're really getting at is we want to start some of the calculus of what we've been doing for the last few days with rectangles. Riemann developed that plan that said if we take the sum of more and more, tinier and tinier rectangles that we fit under the curve, we can get to the limit when those rectangles shrink to having a base of 0, or almost 0. And in calculus, we could get to that limit for what that value representing the sum of all those areas under the curve would represent. So far, you've done all curves that have been positive, meaning all of those rectangles formed have been above the x-axis. We want to keep that in mind so that some of the things that you're thinking about may have to change a little bit when we talk about rectangles that exist under the x-axis. So in the formula that Riemann came up with, this was Riemann's formula for his sums, and this matches what you've been doing the last few days. And that's why if you understand what you've been doing the last few days, maybe we can make a connection here. So what you've been doing the last few days is selecting base lengths, subintervals, that have been the same size. Riemann said they don't have to be, but for convenience in calculating what you've been doing, and then multiplying through. So we've been using that interval length as our length of base. So whatever your interval length, whatever you are having your x's change by. So Riemann said you would have called that delta x. If you use bases of 1 or bases of 2 or bases of half, whatever those sub-interval lengths were, then you guys were using the function to find the values in order to have heights. And then you added up those heights so that you could multiply all of them by the base at once. So delta x that Riemann's got in his formula is what you had basically as your base length. The length of n equal subintervals then is our delta x, or our base for all the rectangles. And that base is what we're going to have shrink to 0. The sum, and you see some summation notation right away, you see the sum of the function values for subinterval 1 through as many as you have would represent that sum in parentheses you did of the heights. So all those different function values right here that you had added up from the different intervals, that's what he's talking about in this notation, the sum from the first interval until the nth interval of those heights that came out. So when Riemann puts it together, it's exactly what you did. Right here, these are your base values. These are the sum of all your heights. So he said the limit when those intervals in between, the lengths of the bases, get so small that we end up with a lot of tiny rectangles to fit that curve is this sum that he's talking about. The graph underneath just lets you see some more of that notation. And if you want to pause here and compare so that you can see that those c sub k's are just the different intervals. And then the f of x values, or the f of that c sub k, is just the heights at those different locations. So where this is moving towards in the calculus is this idea called a definite integral. So a definite integral, and if you read in here, and you can read this, pause the video, and sort of see what you can take from the notation in the dark that I copied from the book, saying if this limit exists, if when I make those rectangle bases really small and I have infinitely many of them, if they settle on a number as a limit, no matter how we split up the area, then the function has a quality that we say we are able to integrate the function, has an integral, a definite integral. And that integral is that value that we found, that summation of all the pieces under the curve. So theorem 1 is an existence theorem. Theorem 1 that goes along with this says all continuous functions have this quality, that every function that you know that's continuous will be able to do this. I'll be able to take a portion under its curve between the x-axis and the curve. Again, talking mostly ones that have their values above the x-axis. If a function's continuous, then I definitely can get this idea. I can definitely get that that limit to come to a single number, and it has an integral value. So from A to B on a continuous curve like this, it is absolutely possible through that limit with the Riemann sums to come to one value called its integral. It is possible to happen on a discontinuous function as well. This theorem guarantees that it works for continuous functions. It says nothing about functions that aren't continuous. Some functions that aren't continuous will be able to do this. You saw the greatest integer function yesterday in warm-ups, and you were able to come up with a sum, in fact a definite sum, because you weren't approximating, of that area between the curve and the x-axis. So some notation you'll need. Riemann used the Greek notation with the sigma, the delta, and those things that you've seen in what we had before. So Riemann's notation is the one that was on the previous screen. Leibniz was kind of a notation guy. He used Roman notation, so it looks a little different, a little sleeker, if you will. But he's saying the same thing. So let's see if we can translate it. So the sum of those n rectangles was the limit as those rectangle bases got really small, and he said we're going to call that the integral. And it looks like a hook. It looks like a very stretched out S. Our lower bound goes here, and our upper bound goes here. Those are those places on the x-axis that our interval is actually, the bases all fit between those two x values for your interval. The function that we're using to generate the heights of those rectangles, and dx is just the notation that he's using for delta x, the summation of your function values in a much sleeker way. So that function that's in there is called the integrand, the one that we're using to integrate or get that integral value. And your variable here, your variable could be lots of things, but it's whatever you're doing your integration with respect to. So if your function's in terms of x's, then your variable of integration is x's. It sometimes uses a dummy variable, for instance, f of g, f of w. It could be anything, but then your integration variable should match. When you found a value, that limit value, then you have evaluated the integral and you found that area under between the curve and the x-axis. So let's just change some notation. And again, pause the video when you need to, so that you can slow this down, take it, and then check to see if you're doing all right. We're not evaluating them yet and getting numbers. We're just saying, how do you take the limit notation here for a specific interval and change it into that sleeker Leibniz notation that lets you see it a little bit differently. So this one would look like the integral from, and our integral will go from our interval, the integral from x is 1 to x is 4. Our function then, our function's right here. C sub k's are our x's. Those are those lengths of our bases. So there's our 1 over x is that function, and that dx represents our delta x. So that's how we write that integral from the Greek notation to the Roman. And we're going to mostly use this nice integral notation right here. We have to understand that it came from that limit notation. So knowing where it came from makes you understand that it's still a limit. Pause the video for a second, see if you can come up with the notation for this one, and then turn it back on. All right, so putting this together with everything we've done so far. So far, we've mostly focused on functions whose values are positive, meaning that the curve has mostly remained above the x-axis. So the first definition, when we define what we mean by this definite integral, is defined first only for function values that are non-negative, meaning the entire function stays above the x-axis. So something like x squared minus 1 would not be what this is being used for at the moment. We'll stretch the definition to meet those needs soon. Let's only talk about functions whose curves are above the x-axis completely. So therefore, if it's not negative, and if we are able to integrate it over a closed interval, meaning we can do Riemann sums and come to that limit, then the area under the curve is represented as this definite integral. The actual area then is the same value as the integral. So area for functions that are always positive actually is the value of the integral. So sometimes when you're asked to evaluate an integral, one way to do it is if the function always stays positive, is to just evaluate the area between that positive curve and the x-axis. The next drill down describes, well, what happens if the function's values don't stay above the x-axis. Here's where we just have to be really practical. Area is never negative in geometry. So just consider that for a minute. You never found an area that we reported as negative. So area itself, if the question is about area is always positive. However, if we are asked to find the limit of adding up the total of areas that represent something like locations, represent something like production, okay, if we lose location, we back our car up, or if we destroy something and we have fewer of them than we did before. So area always positive, so if we evaluate an integral and part of its area is under the curve, in the total, that area is going to count against the total, against this sum. So if this sum comes up negative, meaning we have more area under the x-axis and the curve than we do above it, then we'd have to put it in its opposite in order to report area as positive all the time. So it's absolutely possible for our integral value to come up negative, because it means that the sum of all those pieces had more pieces under the x-axis than above. But if we're just reporting area, then we'd have to put an opposite in front of that number in order to report area, because area is always positive. So the integral of a constant. So if, and we've seen this before, you've actually done these problems before, just not as an integral, so let me show you what it might have looked like. If we talked about something moving at a constant velocity of 75, let's say miles per hour, from time 1 hour to 4 hours, you already knew how to evaluate this by finding the area between that function and the positive function and the x-axis. That's what this is saying. So this is saying if I wanted to do this problem as a definite integral from 1 to 4 of my function that's a constant, 75, then with respect to x, then my actual value is something I already know how to calculate. It would be that constant times the difference in my interval values. And that's what this is saying, my constant times the difference in my interval values. So I'd be looking at 75 times 3, 225, and then throw a unit on there that's representing what this is. In this case, if this were miles per hour and hours, then my unit would just be miles. And because all of my rectangles are representing positive travel, then all of those miles add up to that. Integrals tell the area between the curve and the x-axis, sort of. So what they do is they tell the net area. Net meaning, and we mentioned this word in class the other day, the sum of the pieces with their signs, positive and negative. So when it asked us to evaluate integrals for the constant function, integrals could be positive, they could be negative. So this is a constant function. So there's our negative 10 from 0 to 3. So when you think about the area for this, my function would look like this, and I'd be asking for the area from 0 to 3. And that area itself is positive. Area is always positive. However, by location, That's negative 30. So integral negative 10 from 3 minus 0. My integral's value then is negative 30. If the question were what's the area between the curve and the x-axis, the area is positive 30 because, let's go back to this rule, it says the area is the opposite of the integral value when the function is below the x-axis, when the function's values are all negative. So make a distinction, it's not always that the area and the definite integral match, in fact sometimes they won't. So the next one down, let's see if we can evaluate this one. This one looks odd because it says dr, but there's no r in this function, it's just pi. Well, this one says dx and there was no x in the function. So in this sense, it's sort of serving as a dummy variable because it's not going to matter. This is your rate, your constant rate of pi. So that same rule for finding the value of the integral, constant times the difference in my interval. Okay, so we're looking at pi times square root of 27 can be simplified. So we're looking at 3 square roots of 3. So the value for this one, pi is completely a positive function, so this should be positive to begin with. 2 square roots of 3 pi. In homework, you might be asked to use the graph in order to evaluate the integral. So one that you might not be a constant. We still have to think about area positive versus the integral could be positive or negative. So for this one, it's asking us for the interval from pi to 2 pi, what's the definite integral of theta d theta? Theta d theta would be the same as if we asked you x dx. Your function is y equals theta or y equals x. So the graph then is that constant function that runs, well not a constant function, it goes 0, 0, 1, 1, 2, 2, 3, 3, pi, pi. So it runs at that 45-degree angle between the x-axis and the y-axis. So between pi and 2 pi, we can use the area under here to evaluate it because for positive only functions, and this part is positive, the area between that curve and the x-axis is the value of the integral that we want. So we've got a trapezoid in there. You can also break that up into separate areas if you'd like. But that trapezoid has a height of pi because the function says that the theta value is the output value. So here's your theta axis. So at theta is 2 pi, your y value or your output's also 2 pi, 2 theta. So for my trapezoid, I have bases of pi and 2 pi. They are pi apart. So if I'm using trapezoid, 1/2 sum of my 2 parallel bases times my height. So I'm looking at 3/2 pi times another pi, 3/2 pi squared for the value of that integral. This one's a semicircle, but again, all my areas above the x-axis, therefore my area under the curve does match the value for my integral. So I'm going to use that in order to evaluate this area. This area is asking from -3 to +3 on this semicircle square root of 9 minus x squared with respect to x. What is that integral value? Again, because it's a positive function, we've got that rule, and I keep flipping back just so you see them. The rule is for a function that's completely non-negative, the integral can be found by finding the area between the curve and the x-axis. Too far. So area for my semicircle here then, it's going to be 1/2 pi. My radius here is 3. So 9 pi over 2 is my integral's value. Last thing on this video is your calculator can do an approximation for a definite integral. Again, it's only an approximation numerically, just as when it numerically approximates derivatives. So this isn't evidence that can be used. This is evidence that can be used to check, to evaluate an integral, to see if you're close. So on your calculator, please find under the math key. If you have an updated operating system, when you use 9 under the math key, it's going to give you, it looks like it says function int. That's on a TI calculator. Your book is going to call it NINT, the numerical integral value. Your calculator calls it the function's integral. On the updated operating systems, it actually pops up what looks like a definite integral setup. If you have an older operating system, it's gonna just bring up that command in some parentheses. So I'm showing you on the screen down here what it would look like to evaluate this integral from -1 to 3 of the function x squared times e to the negative x dx. Okay, on your calculator screen, you can see, or on my calculator screen, you can see how it enters if you have the updated operating system with the notation like that. Otherwise, you can see what it would have to look like if you have the older, and I'd be happy to help you update your operating system. And it says that approximately comes to 1.872 if you had to put it to 3 decimal places. All right, we're gonna pause here, pick up on the second video.